Welcome back. I think we have started drawing the trellis diagram in the last class. For given input, if the input is 0, we have labeled it as with some branch with a black one, and if it is 1, it is labeled as the red color, right? I think we have done that way, and we have completed all the trellis diagram. I think most of the people, they have done it even in the homework also. And I ask you to label the corresponding output also on each branch. I think that is also done by some people. Let me share my content today. Yeah, please, are you able to see the screen, please?
Yes, sir.
Okay, this was the last class discussion, and this is the trellis diagram what we used for the given example, what we have taken based on the state machine diagram. So, based on this state machine diagram, we could we could do all this trellis diagram, okay? And let me give you the complete diagram which I have drawn again. And please verify your results with this, whether this trellis diagram is matching your trellis diagram or not. Please find out that, okay? Is it okay? Slightly, yeah. Is it convenient for you now? Is it? Are you able to see this clearly? All of you? Hello?
Yes, sir.
Yeah, please verify your results. I have given you this black indicates the input is when the input is to the system, whatever we have assumed that the convolutional encoder or half rate encoder, when the input is 0, we are indicated with the black color, and whenever there is a 1, we are indicated with a red color. This is what we have indicated here. Please see that in the bottom I have given you the corresponding what you call result kind of thing. For input we are using a red one, for input 0 we are using a black one, and the outputs are labeled on the top of each branch, or we can call it as a link or branch. So please remember, each one we call it as a link or branch. Okay. So on each branch, the corresponding output we have given based on the trellis diagram, or based on the state machine diagram what we have got for the given convolutional encoder, half rate convolutional encoder. Okay. So these are the outputs on each branch. I think most of them they have done it correctly. And please indicate that, note that T0, T1, T2 indicates what, please? These are all at different time instance, right? And these are the states of the resistors, the states of the flip-flops which are there in the convolutional encoder, and these are at a different time instance. T0, T1, T2, T3, T4, T5, T6, T7, T8, and so on, right? It goes like this. Fine. Now the important point that what we have to check here is, after mentioning the output on each branch, on each link with a green color which I have done, are you able to differentiate this and this one, please, from the diagram? Are you able to differentiate? Or you got any confusion? Let me know. Is it clear for all of you? See, for this branch, what is the output? When the input is 0, when you are changing the state from 0, 1 to 0, 0, what is the corresponding output? Apply 0.
1, 1, sir.
This is 1, 1. So you are able to see that, right? And here also there is a downwards, there is a red line. That is, whenever you are changing the state from 0, 0 to 1, 0 by applying the input 1, the output is corresponding is 1 1. Like that, these are all indicated in this. Okay. Similarly, can just randomly I'm checking. Please tell me the answer. Suppose I'm changing the state from 0 1 to 1 0, 0 1 to 1 0, 0 1 to 1 0, and I'm applying input 1, and input bit is 1. So what is the output?
0 0, sir.
So 0 0. So likewise, you can check up. This is the 1 input 0 0. You are changing the state from 0 1 to 1 0, like that. You can see all these diagrams. Now, once it is over, with this, the greatest advantage now, let us say my sequence, I'm writing here, UK1 and UK2. Okay, this I'm just taking some example. 0 0 0 0 0 0. Let us say these are my zeros. What is my corresponding output? And to move on, see, this is my 0. I'm starting point here. 0, that means 0. This is my output. So this is my output. So my output is simply 0 0 0 0 0 0 0 0 0 0, like that it goes. So from the Trellis diagram, I can directly find out the output. I did not refer to the state emission diagram and then find out what is the kind of output. Okay. So the corresponding output will be VK1, VK2. So what is the corresponding output? So you will get, for every single bit, you will have a pair here, 0 0. Again, you will have a 0 0. Okay, let me give you the.
Sir, input is only one bit, no, sir. UK1 and UK2.
Which one? Oh, sorry.
Input means only.
Sorry. Yeah, you're right. You are only UK. It's not a UK. You're right. Thank you. So your UK is only one bit. For the corresponding bit, you are getting 2 outputs. Correct? Initially, we have started with all the registers are loaded with 0, and you will get corresponding output. Likewise, you will get 0 0 0 0 0 0. It goes like this. Okay. Now, if I give you all ones, tell me, let us say my inputs are all ones. So what is my output? Let us see my UK is equals to all ones. 1 1 1 1 1 1. Let me see 1 2 3 4 5 6. Okay. However, so I'll keep, let us say, 2 zeros at the end. Let us say. Can somebody tell me, by using this Trellis diagram, you can easily find out what is the corresponding outputs. VK1, VK2. Can somebody tell me, please?
1 1 0 1.
Yes, please.
1 1 0 1.
So this is 1 1. See that you have to follow this path. 1. See, this is 1. So that is 1 1. Yes.
0 1.
Next, this one is 0 1. Very good.
1 0
1 0. Very good.
1 0
1 0.
1 0
1 0. 1 0.
1 0
So this is for 1. This is for this. 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 Okay. After that, for 0. For 0 from this diagram.
0 1 sir.
0 1. Very good.
0 1
And 0 1
can you please call it up sir? 1 1
is 1 1. That is enter.
yes sir.
Okay. Now the question is why I am stuffing 2 bits at the end zeros. Why? Why should I stuff with zeros?
Make the registers clear.
Yeah, I want to get back the state of the convolution encoder back to the normal state, back to the initial position. That's why once my bit transmission is over, I'll stuff with the number of zeros at the end so that it will come to the initial state. That is the reason. Is it clear, all of you? Actually, I am transmitting here 6 bits, 6 input bits here. After that, don't have any bits. So what I do, I'll stuff with zeros so that it will come to the state. So this is something like this is starting point. Okay, this is starting point, and this is ending point. Okay, this is the normal conventional way. Whenever we want to get back the system to initial state, then I'll stuff with zeros, depending upon the number of flip-flops that we have in the encoder. Okay, if you have got 3 flip-flops, I have to stuff with 3 zeros. If I have a 4 flip-flops, I have to stuff with the 4 consecutive zeros, like that. Okay, is it clear up to this? All of you?
Yes, sir.
Now, I'll take another different input now. Tell me what is the corresponding output. Okay? My input is, let us say my input is yeah, here you go. Let us say my input UK is 1 0 1 1 1 followed by 3 zeros. So let us say this is my code, and last 2 bits are actually zero stuffing. That is, I'm clearing out. I'm getting the system into the initial state. The last zero. Actually, these are my bits. Okay. Can somebody tell me what is my corresponding output by seeing this Trellis diagram, please?
1 1
1 0. Let me write this one. VK 2. Okay. So tell me, ma. Yes. 1 1.
1 0
Other people, please. Somebody can. Basha, please wait for some time. Let other people give me the answer.
okay sir.
Okay, please. Other person, please. See, follow this path. 1 1. Let me use the different color. Let me use this different color. So the first one is 1. Next one is 0. That means I am going with this path. That is output is 1 0. What is the next one? It is 1 1. It is actually next one is bit is 1. So I have to go this way. So what is the corresponding output?
0 0
0 0. What is the next one? It's 1. So that means I have to go down this way, right? This is a 1. So from here, so what is my output here?
0 1 sir.
So 0 1. For the next one, Here he goes. You have to go like this, right? 1 0.
1 0.
Then for this 0, you have to go up, right? This is a
0
0.
1.
So 0 1, very good. 0 1. And for the another 0, here. This is another 0 here. 1 1, right?
1 1. Oh.
And finally 0 0 for 0. Correct?
Yes, sir.
Agreed. Agreed. So this is my output base. So from the Trellis diagram, because we have done all possible outputs, we have done for all the possible inputs, possible outputs, we have done this, and based on that, simply we follow the path. That's it. That means what is the path now? I think it is going like this, like this, like this, like this, like this, like this. There is the important. So see that 1 0 1 1 1 0 0 0. So for this kind of input, this is my corresponding output. Very simple. So the Trellis diagram will give you beautiful insight. Directly you can take the output from this. Is it clear, all of you?
Yes, sir.
Okay. Now let us introduce some errors in the received sequence. Now this is my transmitted signal. Okay, this is my transmitted signal. If I introduce some errors in this, I'll get the received signal. Correct? Let us say this code word is transmitted through a binary symmetric channel, a simple additive white Gaussian channel, where it's a binary symmetrical. That is, the probability of occurrence of 0 is equals to probability of occurrence of 1. So if that is the case, I call it as a binary symmetric channel. When I transmit this kind of code words through a binary symmetric channel, because of some noise, some bits are in error. Okay, let's take that particular situation. Is it clear? Okay. Now I'll give you that situation now. Can I make it bigger? Slightly bigger? Okay. Or is it okay? I think this is we have discussed, right? For all ones and for all zeros, the outputs are the same. Okay. And this also we have discussed. Now, I want to make the errors that are to be introduced here. Okay, let me do right. Now, this is our code word. We get the output here, output sequence. This is my output sequence here. And now what I do, I'll make some errors here. Let us say this bit is an error and this bit is also an error. Let us say these are changed and then we are getting this is the received sequence. See that 1 1 is same thing. 1 0 same thing. But here 0 has become 1 here. That's why it is 1 0. And this 0 1 has become 0 0 because there is a change in the bit 1. And the rest of things are same. We are so let us say this is my received sequence. How this trellis diagram is going to be help us to in detecting the what do you call the appropriate the transmitted sequence. Okay, for that what we have to do is we have to use the maximum likelihood decoder. We have to use maximum likelihood decoder in the sense we have to choose what is the corresponding the closest code word possible from the Trellis diagram with which is matching to the received sequence. We understand what I am trying to say? What is the meaning of maximum likelihood decoder? The maximum likelihood decoder is a decoder which will give you the output, which is, you see, we got all the possible outputs here. We have got all the possible outputs, and out of all these possible outputs, which is the closest to this received sequence. So that is what is known as maximum likelihood decoder. Is it clear?
Yes, sir.
Now, in order to find out that maximum likelihood decoder, we need to find out the minimum Hamming distance. See, we have to match the all possible code words, which is the closest one. That means I have to find out. See, how many possible code words are there here? Output code words. Can somebody tell me how many possible code words that are there? Here. That depends upon the input. You will have so many 2 power k. You got a possible code words. So every possible code word you have to write down. So you have got a set of all code words possible, transmitted possible. Now in that you have to select the best one, which is having the minimum distance, minimum Hamming distance with respect to the receiver sequence. So in that also in the receiver sequence we take the pair of weights, because we are getting output the output 1 and output 2. We take the pair of outputs and then we'll try to match which is we try to find out what is the minimum Hamming distance. Okay, let us find out the Hamming distance with respect to the receiver sequence with all the possible code words. You get my point? This is a very crucial point to understand. In order to go for a decoder, we use the maximum likelihood decoder. So the maximum likelihood decoder will be possible only when we match, or we are trying to match which is the very closest possible code word, which is very close to the received sequence. That means for that you have to verify every code word, possible code word with the received sequence. And how do you verify? The verification is possible only through the Hamming distance. So whichever code word gives the minimum Hamming distance with the received sequence, that will be the best match possible. Okay, thereby we will be finding out the minimum probability of error with that. We will get a minimum probability of code word. Now we are not talking about the minimum probability of bit error. Now we are trying to find out the minimum code error, code bit error, code word error. Okay? Is it clear?
Yes, sir.
Yes, sir.
Lahari, are you there? No.
Yes, sir.
Lahari, tell me, ma, did you understand?
Yes, sir.
So what exactly you are doing? Tell me. How are you doing the decoding? You tell me now, whatever you are understanding, let me know. Lahari, please explain. I want to know your understanding. Otherwise, I want to explain once again, because this is the crux of the decoding part. I am waiting for your response, please.
Explain once again, sir.
Okay. See, we got the code word, and I am purposefully, let us say this is my received sequence. Let me check. Yeah. This is my received sequence. Okay. Now, with this received sequence, what I'm doing, I want to match the close match. If not correctly, because there are some errors, I want to check which sequence, which code word sequence is very close to this received sequence. This is my decoder, maximum likelihood decoder property. Maximum likelihood property means every code. See, now how many code words are possible in this? I'll take up an example here. Let me look at it. See, let us say one possible code word is all zeros, 0, 0, 0, 0, 0, 0, 0, 0, like this. Okay, this is one code word. Another code word is, let us say this one, again this one, this one, this one. Another possibility, correct? Another code word could be this one. So I'll draw with the other one, the other color. I'll draw with another color. Let us say another code possibility is, another code word is, I'm drawing with the help of the yellow color, not exactly yellow. Okay, let us say this one. Okay, this one, this one, this one. Okay, and then this one, this one, this one. Let us say another possibility. So how many possibilities I have shown here? 3 possibilities. One is all zeros, the other one is with a blue color, the other one is with yellow color. I can have likewise all possible code words, correct? Those can be transmitted. Now my aim is, I have received some sequence. I want to find out the closest possible, because I know the receiver knows all the possible code words. Receiver has got a big data, big possible, now a table of all possible code words. Now in that, the receiver has to select which is the best match for the received sequence. How will you find out that best match? Only by finding out take the receiver sequence, and then finding out, let us take one code word and find out what is the minimum distance from these two. Minimum Hamming distance. So likewise, you have to find out what is the minimum Hamming distance between the received sequence and with all the possible code words what we have. So whichever is very close, whichever is showing the minimum Hamming distance, that will give you the closest transmitted sequence. And with that, we will get the minimum probability of code word. So we wanted that kind of output. So that is the property, that is the job of the maximum likelihood decoder. Lahari, is it clear?
Yes, sir.
Okay.
Yes, sir.
Now what we do is, we will go that. So for that matter now, I have to find out the Hamming distance between receive sequence and a selected code word. How many such code words are there? All possible code words. Whatever the all possible code words for this kind of system, I have to verify with each and every code word, find out what is the Hamming distance between the received sequence and the code word. And likewise, I have to find out with every code word the Hamming distance, and whichever is showing the minimum Hamming distance, that is the closest sequence with the received, closest with respect to the received sequence. Okay, that is the ultimate aim of that's our goal basically. Fine. Now in that process, what we do is, we will find out the Hamming distance between this received sequence and each possible code word. Okay, shall we do?
Yes, sir.
Okay. Now let me give you some kind of this thing. Okay. Can somebody tell me what is my received sequence which I showed? Yeah, let me draw here. Okay, one. So let me give you here so that it will be useful, and by seeing it I can write. So my received sequence is RK, RK1 and RK2. this is equals to, let me write the received code word 1 1 1 0 1 0. I'm writing pairwise so that it will be easy for you to understand. 0 0, then 1 0, then 0 1, then 1 1, then 0 0. Okay, this is my received sequence. Okay. Now, in this, what I do, I'll do something which is convenient for you. I'll do that some partitioning so that it will be easy for you to analyze. I'll do partitioning. Okay, how many partitions are there? 1, 2, 3, 4, 5, 6, 7, 8. Correct? Now let us take the first code word, all zeros. Okay. So in this, now I want to make use of.
Sir?
Yes, please.
Sir, it will be more easy to do this one, sir.
Which
If we
one?
go along this line.
Yeah, we'll come to that point. We have to do that. So before we go along with that, first of all, we must find out each link or each branch, what is its Hamming distance between each code word. We have to find out that. Then we do, as you said, we have to go that way only. Which is the minimum Hamming distance? Which is the path having the minimum distance, Hamming distance. Is it okay? Fine. Now let us start with this. Here, what is my output? I think it's pale. Are you able to see this color? Which color you want? Let us say maroon. I'll use maroon because this is the mostly very popular color among ladies. My wife uses maroon color for this thing, no? What is that? Tilakam. Okay. So this 1 1. See, you compare this 1 1 received sequence 1 1 and 0 0. What is the Hamming distance between these two? Can somebody tell me? I'm taking 1 1 received sequence first pair 1 1 and this pair 0 0. What is the Hamming distance?
2, sir.
2. So I write 2 here. And the branch I am writing 2. Similarly, 1 0. I am comparing 1 0 and 0 0. What is the Hamming distance? 1. Correct? Here also 1. Here also it is how much?
0, sir.
Very good. 0. Then here 1.
1, sir.
And then this is 1. Correct? And here, tell me.
2.
Very good. This is 2. And this is
0.
So likewise, I have to find out the Hamming distance. I have to label onto each branch or each link with the Hamming distance. You have to do that exercise for the complete Trellis diagram. Okay? Let me give you one more example. Let us say 1 1 here. I go this way. This one, this path. All red colors, all 1 1s. This branches, no, all these things. So I'll go 1 1 1 1. What is the Hamming distance here?
0, sir.
0. Very good. 1 0 1 1. What is the Hamming distance here? 1. Right? Hamming distance is 1. Correct? Again 1 0. 1 0 0. What is the having distance here?
2.
2, sir.
2. What is the having distance here?
1, sir.
1, sir.
What is the having distance here?
1,
1,
sir.
sir.
What is the having distance here?
2, sir.
2. This we will solve. So likewise, you have to proceed all for all branches. You have to label with the having distance. Will you do this exercise?
Yes, sir.
Okay, will you do this exercise now? Once you do this exercise, then I will talk about how to find out the nearest code word possible. So please do this exercise, all of you. So let me see. Can somebody tell me for these blacks? Can somebody tell me what is the having distance for these blacks? You start from here because this will not work. See, this will not be there. Okay, this will not be there. You have to start because we are starting from here and we are ending here. Every time you have to start from here and then you have to end here. Please remember that. Okay. Now this will not be useful item, and this also is not a useful item because this is the starting point. Next sequence only it comes here, not comes here. Okay, because there is a time. Say when this is a T0, obviously in the T1 time it will not come here. This will come here. So therefore you have to go this way. Okay, the first possibility is now 1 0. So correspondingly you have to select this one. Correspondingly you have to select this 1 0 because this is the T1 time. So you have to choose this. Now, this is not the output now. Now we have to choose this because we are in the next stage. So 1 0. This is 1 0 1 0. This is you are having distance is 0 here. Black ones I am talking. And then 1 0. This 1 0. Again this is having distance is 0. And then this is 1 0. So what is the having distance here for this?
1, sir. 1, sir.
So 1 here. Having distance here?
0, sir.
0. Having distance here?
0, sir.
No.
No, no. 2, sir. 2.
2, sir.
Yeah, this is 2. And here 1. Correct?
Yes, sir.
So likewise, you complete this process, and let us see the upper one. Let us see the upper one, which is going up. So what is the having distance? See, you are starting from here again. When you are starting from here again, you have to start with this. Okay. So 1 0 and 1 1. What is the having distance?
1, sir.
Having distance is 1. Okay. Next 1 0. 1 0 and 1 1. What is the having distance? 1. What is the having distance here? 2. Because this is 1 1 and this is 0 0. Correct? Are you able to understand this point?
Yes, sir.
Sir.
So likewise, you please proceed further and find out what are the having distances. In the next class, I am going to tell you what is the how to decode. We call that decoding algorithm is called as Viterbi algorithm. Viterbi. The person, the person, the engineer who found this kind of algorithm is called as Viterbi. VI. We will talk about that in the next class because I got a call from Vice Chancellor. I need to go now. Okay. Viterbi algorithm. Please work it out, all of you. And I request all the students to keep this chart. You can do one thing. You can forget. You can redraw a particular separate what you call trellis diagram without these outputs, so that you will get some clarity. You keep only the having distances. Is it okay? See, you must have at least two diagrams. One is trellis diagram with outputs, okay? The other trellis diagram with only the Hamming weights, Hamming distance. You label it only with the Hamming distances so that in the final, when we are understanding the output Viterbi algorithm, it will be easy for you. If you have only one trellis diagram, it will be too complex because every time you are indicating all the things on the same diagram. So that will give you a lot of confusion. So I request all of you, each one of the student, each one of you, please prepare 2 trellis diagrams. One is exclusively for all this indicating the 0 and then one the same red and black and only the outputs. The other one is you draw another trellis diagram with the red and black. Only thing is you have to mention only the Hamming distances on each branch. That's it. Okay? So please do this exercise. We'll continue in the next class. You please tell me. And you know one thing. In IS examination, recently in 2017, I think 17-18, yeah. They have asked about the Viterbi algorithm. What kind of what is the meaning of that? And they have asked for 10 marks and draw one trellis diagram, explain the Viterbi algorithm for one sequence. They have given one sequence and then they have found they asked us to find out the correct sequence. So decoding part. They have given the diagram. The funny thing is they have given the diagram and then we find out what is the corresponding. So that way you can save the time. Fine. So we'll wind up here.